Morning, everyone. As I've told you yesterday, today we're going to have like a quiz. So the quiz is going to concern basically lecture 3 and lecture 4. So before we get there, we'll go through like a small revision. But I think we should wait a little bit longer just so that at least the majority of you are here. Okay, are you guys hearing me well?
Yes.
Okay, nice. Yeah. So let's just wait like 3 or 2 more minutes and do a quick revision for basically lecture 3 and lecture 4. And from there, I'll open the quiz for you. You guys cannot see the quiz yet.
No, we cannot.
Nice. So after that, we'll just give you guys the quiz and you get good grades, hopefully. And from there, we will finish our, we'll repeat the first part of lecture 5 and then finish basically the lecture 5. And from there, we would open up like a small revision, what is it called? A session, so that you guys could prepare for the midterms. So if you guys have any questions, maybe have like something you would like to test out, something you would like to do, you would like to get some preparations for the, what is it called? The midterms? Yeah, this is the time.
I'm sorry, could you please repeat one more time on which week we will have the midterm exam?
Didn't hear the question?
On which week we will have the midterm exam? I'm sorry.
On which week we will have the midterm exam?
Yes,
That's
yes.
a good question. Let me, so the 13th of September. 13th.
Okay, okay.
Like after 1 week and a couple of days. Has Karam already shared with you guys the, let me share it again, maybe. There you go. Has he shared with you guys this one? So just like quickly to go through it. Yeah, assignment 1's upload has already started. Today, he will speak to you guys about the project. So basically what it is, what are the different accepted projects that we will, he will allow. And basically the assignment submission should finish around the 6th of September. The second assignment will be on the 9th. And of course, the midterm will have its own week. After that, we will like take the, get back the assignment 2. And then assignment 3 will be on the 20th. And on the 22nd, we're going to expect like, what is it called? Like a small checkpoint for the project to make sure that you guys are not waiting for the final day to basically start working on your project. And then for the final assignment, so assignment number 3, it's going to be on the 27th. So I understand that like this period of 27th and 22nd with the homework 2, homework 3, and the project is going to be very busy for you guys. So we decided to give you assignment 3 and assignment 2 like super easy. So it shouldn't really take any time from you. The project submission will be on the 29th of September. And of course, your final exam will be on the 6th. Before we get the final exam again, we'll also have like a revision session, both for the lab and for the lectures. Does that answer some of your questions?
Yes, thank you very much.
Sure. So let's go just like a quick revision over lecture 3 and lecture 4. So basically lecture 3 speaks about image segmentation, right? So we spoke that, we said that the first one would be image binarization, which is just setting a global threshold and basically thresholding the image on it. And this would give us like some sort of a mask of the image where we have the, let's call it the foreground highlighted and the background hopefully would be completely eliminated. So we said that there are different techniques for thresholding. The first one that's interesting for you is the bimodal histogram. So assuming that there is a foreground and a background, this technique allows us to basically draw or plot the different histograms of intensities of the pixels. And we will notice that there are two peaks. The first peak represents kind of the distribution of the background or the foreground, and the other one represents the background or the foreground. So one of them takes one and the other takes the other. So here we said, once you have this one, the question now is, how do you choose basically which point to split on, right? So visually, we can easily see that it's this point, but there is no way to kind of build an algorithm that works on this visually, right? So this was the task of Otsu's method. So Otsu's method is a very simple algorithm that basically tries to automate this process of what you would do and basically what's happening in your brain while you chose this threshold in here. So the assumptions, or the only assumption it makes, is basically that the image has a background and foreground only. Like there are two main classes. So there are images, for example, like this, let's say, I don't know, where the background itself kind of is a foreground, right? So basically you're looking at an image of the sea. So in this case, like there's nothing that you could call as background or foreground. Everything is the same. And there are, of course, images where you have lots of a lot of moving things and stuff, right? So just too much foreground and the background is kind of not there. And this would give you like the second assumption, which is that the image is a bimodal, which contains two peaks. So the goal of the Otsu's method is basically compute the best threshold. The best threshold is defined using these two criteria, basically the smallest within class or intra-class variance and the largest between class, intra-class variance. So for example, if we split, let's say here, the standard deviation here is going to be small, but the standard deviation here is going to be huge. Same thing if we split, somewhere around here, this standard deviation would be too big, this one would be small. Hence, the best one would always be like here, where the standard deviation is smaller from this side too. But this is just like a small explanation. And we said that there are two types of, or like two extra kind of enhancements over thresholding or global thresholding. One would be this band thresholding, where you have two thresholds instead of one, and you take it as one if it is within this band. And there is the semi-thresholding, very basic idea. Basically, instead of putting a 1 here, you put the value of the image itself. Then we saw that there might not always be a good global threshold for every image, and hence something like adaptive thresholding was invented. Basically, you go through the image in like different windows, and for each window, you give it its own threshold, right? So this allows it to, for example, if this place is much darker than, let's say, this place, you will still be able to kind of threshold the background and the foreground regardless. So here we can see that clearly the color of the background in this place and the color of the background in this place are super not the same. Nice. After that, we spoke about image gradients and how they're related to edge detection. An edge is basically a place where the intensities are changing very fast. And that's something that you can detect using, of course, using what is it called? Derivatives. One person would say I could also like detect it using, what is it called? The difference, right? So if I'm within like pixels that are in like tens, right? 10, 10, 10, 10. And for some reason, like this, 10, 10. For some reason, I moved to other pixels directly, which are in like in the 200s, right? I can easily guess that there is an edge here, right? How do you do that? I simply do the difference between the pixel values. Yes, exactly. That's the same idea, basically, of using derivatives. Your idea is correct. So basically, if you wanted to just do the difference between the values or the intensities of the pixels that are neighboring each other, this is where what derivatives are doing for us. So basically, the only difference is that you no longer need to basically give that threshold, right? If the difference is higher than a certain number, then you do something like that. So this is the only thing that derivatives kind of take away from you, and you just focus on finding something that crosses zero instead of finding something that's working in certain criteria. So edge can be detected, of course, using the first derivative or the second derivative. As we have said, the first derivative allows you to see these peaks in the edges. So basically here you see that there is a very large change, and here also, but like there are different. So here you're going from something dark to something white, and here you're going from something whiter to something darker. And of course, for the second derivatives, what you have here is just a crossing of zero, right? So basically you went up and then suddenly you're going back down. Nice. So we said that, of course, the derivatives cannot be calculated because we're not working with a continuous function. We're working with a 2D discrete function. Hence, we don't have just one value for the derivative. So for example, at this pixel or at this point, there's not just one value for the derivative. Of course, there are two derivatives, right? So this is what we're already expecting because it's a 2D discrete function or 2D continuous function for that matter. It's going to have two basic partial derivatives, right? So this is the first difference. And the second difference, it's a discrete function. It's not a continuous function. So we cannot use this formula. Hence, we just approximate it using the finite difference approximation. There are many ways to do that. Here are the three main approximations. Of course, using whatever formula you have, you could calculate the, or you could, calculate, what is it called? The first and second derivatives pretty easily. And usually it comes up to exactly what we have said, or the basic idea that we have discussed, which is just the small difference between the consecutive values. And that would already give you what you are looking for. Yes. Mm-hmm. And then we discovered that basically after you simplify this finite approximation, it turns out to be either like, f of x plus 1 minus f of x, right? So it's basically 1 minus 1, right? Just a simple weight or a simple linear combination of consecutive values of the image intensities. And this is exactly what we are always doing with kernels and these filters, right? So convolution allows us to kind of automate or speed up this process of calculating the derivatives in the x and y direction. And this is the idea of Sobel. So Sobel decided to kind of combine the derivative filter, which is this one, with the basically with the smoothing filter, right? Or the blurring filter. One good question would be, why would he exactly do that? Simply because it would allow you to get, let's speak about blurring a little bit. Why is it good for most of these filters? So for example, here, you're trying to look at this pixel and at this pixel, but when you do some blurring with it, so this pixel would kind of be representative for this kind of neighborhood, and this pixel would be representative for this neighborhood, and you would get much better like derivatives, right? Something that's more general. Of course, there is a horizontal or x-axis filter, and a vertical or the y-axis derivatives filter. In the end, you would end up with two, what are they called, images of the same size as your initial image. And basically what you just do is simply calculate their gradients and compute their direction, calculate these gradients and from them compute their direction and amplitude. Just one second. Yes, these things are very important. Basically, this one gives you the direction of your gradient, and this one gives you the amplitude of the gradient. And these can basically represent the information of the gradient that you are working with, right? So usually the what is it called? The angle is always in a certain range. And for the same range, for example, in this range, you have, what are they called? Gradients of the same or performing in the same manner. And of course, depending on their amplitude, this is kind of their strength. So this way, this is why we use basically the histogram of gradients to kind of represent the information that is inside the images. Yep. There are some improvements of the Sobel filter. So Sobel was like the idea directly, but some other guys were like, yeah, we could improve this filter by changing a little bit the numbers. There's no real mathematical explanation or mathematical basis for this one. It's just basically these work better in other situations. Yep. So this is what basically will happen. We calculate the derivative in the x, calculate the derivative in the y-axis, and then we combine them both in some sort of way. For this manner, what we're doing is we're combining it using this algorithm. Basically, the derivative of I in the x direction is just the value of the pixel in here, and the derivative of I in the y direction is just the value of the same pixel but in the y image. And you just sum them up together like this, take the square roots, and then take the root. Of course, after that, you would have something like this one, but what we are trying to do is basically to detect edges. So usually we just threshold it over something that is a bit better for visual understanding. The Laplacian filter, on the other hand, is trying to basically not use the first derivative, but it's trying to basically use the second derivative. And instead of having, two images for the x and y, for Sobel filter, for the Laplacian filter, we're going to have just one image that kind of combines both of these. So this is what the second derivative of in the x direction would look like. This is the second derivative in the y direction and how it would look like. The implementation of this Laplacian filter is simply obtained by summing these two components, right? And what do we get is this function overall, which is a very pretty function, gives you -4 in the middle, 1, 1, 1, 1, and then 0, 0, 0, 0. And as we have seen with the previous filters, you can always make it better with adding a little bit more Gaussian noise to it, right? Or Gaussian blurring. And this gives you the Laplacian of Gaussians, which is like a very beautiful filter that kind of does both the blurring and the calculation of the second derivative. So this is basically how it would look like, -40 in here, and then just smaller numbers surrounding it until we get to the place where we want. And this is the Laplacian with smoothing. You can definitely see it's not very much influenced by these smaller values. This is the Laplacian without smoothings. It's still good, right? You can definitely see the results, but it's not as good as with the smoothing. Then there is this canny edge detector. Basically, it's just what we have described so far. Adding some smoothing, and then we use different filters, vertical, horizontal, and the diagonal filters or edge detectors. We go through some non-maximum suppression. This is like, we haven't really discussed it so far, but we kind of take the best value at each, or the highest value at every like group of surrounding pixels, right? And then we do some thresholding, and we can, for now, let's go through this morphologies. So we spoke about what is this structuring elements. Yeah, for the structuring element, basically we will go through the image and put it around the image, and depending on the whether we're doing an erosion or a dilation, we will use a certain criteria. So for this one, if the whole structuring element is included in the region, then we take it. If it's and for this one, if at least one pixel is there, then we take it. This one, of course, makes the objects smaller, and this one makes the objects bigger. We have seen how to make each one of them. This is just an example of where you can use dilation, for example, restoring historical data. And we can combine these two operations to do something like opening. Opening is basically you erode, take everything from this image, and then you like construct it back using dilation, right? And closing is kind of the opposite. Basically, the first thing is you dilate, you close these things, and then you erode them to just take away what you have just added. And I think that's it for this lecture, right? Nice. Do you guys have any questions about lecture 4?
No.
Nice. Okay, thank you. Then let's go to the next lecture, which is about, sorry. Right. So in this lecture, it's kind of like an object detection lecture where we'll be speaking about connectivity. So basically an object is a group of pixels that are connected with each other, right? So connectivity, here, for example, we have one connected object, and here we have 4 connected objects, as you can see, depending on whether we're using this 4 connected, what is it called? 4 neighbors, and here we're using the 8 neighbors for. Yes, you can think of this connected component labeling as just like a more or less different, what is it called? Clustering technique. So we have the first pass and the second pass, which is much easily seen here. Yes, yeah. First pass, we see the first one. There's nothing similar to it, so basically, or nothing connected to it already. So we just put a new label. This also, we give it a new label, nothing connected to it. And then this one is connected to this one, this one is connected to this one is connected to 2 of them. There we go. And the second pass, basically, we just combine the different connected labels. So we've seen what object detection is. So basically, instead of just saying there is a person and there is a boat in the image, we must specify exactly which part of the image represents the boat, which part represents the objects, the other objects. Object detection can be like a pretty difficult thing to do, basically for different reasons, such as viewpoint changes, scale changes, deformation, occlusion, illumination, background cluttering, and indirect class variations. Very same problems that you would say that you would face basically in every computer vision problem. Now let's speak about the first idea of object detection, which is template matching, right? So basically, if you have like an image and you want to find out if there is a dog in this image, what you do is you take an image of a dog that exists already, and you just slide it through the original image, and until you find the place where it has like the least difference. Very simple idea. Template matching is based on like a similarity measure, either using MSE or using cross entropy. And then we said that this problem suffers greatly, this solution suffers greatly from scale issues, right? So for example, if the dog here is the main part of the image and your image is much smaller, then you would never be able to detect it. And hence we decided to basically do this subsampling and searching, subsampling and searching, subsampling and searching, and subsampling and searching. Of course, before we apply the subsampling, we do a small blurring, Why do we do the blurring? Mainly because when you are trying to summarize a region of, let's say, 4 pixels, by just taking randomly one of these 4 pixels, you kind of completely ignore the values here. But with blurring, you're able to basically make every pixel a combination of its neighborhood. So if you choose whatever you want, you're still going to maintain as much information as possible. And we can definitely see that in practice. The second part of this lecture was speaking a little bit about HOG, or histogram-oriented gradients. So we said that HOG represents the image as a single feature vector, a little bit big feature vector, but still it's just one. And usually it's used in combination with, of course, support vector machine. Just to ask you guys a small question, you're already very good with support vector machines, right? We're gonna make this assumption on you, and if you're not, then ask Karam to give you guys a small revision about support vector machines, because they will be very important for your midterm. The feature descriptor of histogram of oriented gradients is pretty simple. You take an image of the same size, always the same size, regardless of what it is, you must always have it at the same size. And basically you split it into different grids. Each grid would, for each grid, you will be calculating your histogram of oriented gradients. So for example, this pixel, this is the gradients direction, this pixel, this is the gradients direction, this pixel, this is the gradients direction. One person would say, but like, what do you mean with the gradients direction, right? So basically, in the y-axis, you have one value, in the x-axis, you have another, and basically your gradient is kind of combination of these two. So easily you can calculate your, what is it called? Help me out. The direction and amplitude of your gradient. And then basically you build using, of course, one of these. And then what you do is you calculate the magnitude and the direction. And from there, you split these values onto, well, you would consider it as a histogram, right? Like this. But in fact, it's just, it will be represented in reality as just a small vector, right? Always we have here the same values, right? And this gives us the ability to kind of compare the different features, or like use the same vector or the same vector annotation to basically compare different features and build different image classifiers. The third step will be to basically normalize the gradients over different blocks. So here, for example, we're going to normalize all of these 4 histograms of oriented gradients. And instead of normalizing them alone, we're going to normalize them with their neighborhood. So this allows us to get, so this is what normalizing is. And basically this will allow us to get a set of vectors which are more or less illumination invariant. And ta-da, you have your, so basically you combine all of these features, and there you go, you have your feature vector. And after you add a SVM on top of it, you would get something that works for, that works pretty well for image classification, or later on, we will see it for object detection. Contouring. Contouring is just another way of doing object detection, or doing image segmentation, however you want to think about it, or object segmentation, however you want to think about it. And simply it's fitting some sort of continuous, some sort of a curve that joins all continuous points along the boundary or along the edge of a concept, right, of an object. So usually we try to get something that has the same colors and intensities. The first idea that we have checked is called the snake. And this one allows us to basically first start, give an initial user initialized, what is it called? Boundary, or a user initialized contour. And then the algorithm would kind of start shrinking this user initialized contour until it wraps around something that has the same values of intensities basically everywhere. And the second idea This idea was pretty bad because it suffers from concave boundaries. So concave boundaries are boundaries like this, right? So something where you cannot take any 2 points and link them together, and basically all the points in the middle would still belong to the object. So in this case, we certainly don't have that. But if it was like a circle, any 2 points in here, the line between them will always belong. So this is just like a small revision for concave and convex. And this snake algorithm does not work with concave boundaries. The other variation was the balloon model. So instead of starting from like the outside of the hand, we basically start from the inside of the hand and continue growing as long as we have the same pixel intensities everywhere. And then there is the gradient vector slope algorithm, where we basically are being guided using these different, what are they called, gradients. And this one kind of strikes the best balance between the two previous algorithms and gives the best results. Yep. Nice. So we're quite right on time for the quiz. Now, do you guys have any questions so far? Okay, nice. So I'm going to like set the quiz to start here. Then we're going to close the quiz 10 minutes after this, and we will enable. So the quiz this time is going to have just 9 minutes, right? That's Again, this quiz is open book, so you could always read the lectures and check maybe the recordings, but do not. Can you guys now see the quiz?
Yes.
Yes, we can.
Very well, nice. So just do not cheat and try to basically use this quiz as a manner of evaluating yourselves. It's going to start in like 1 minute, right? In a couple of seconds. Oh. This is bad. I hope I say this. I see that the majority of you have finished. So everybody finished? I hope so. So just a small question. What do you guys think of the quiz? Was it too difficult? Was it too easy? Of course, before you see your grades. Or can you
It was easy, but some questions seemed to me tricky, kind of tricky. It seems that they're easy, but you need to think kind of for them before answering.
Oh, that's nice. That's basically what I was trying to give you. So quizzes are just a way to give kind of free grades to students in order to basically make sure that you guys still get like an A or a B. So basically it should be free 15 points in this course that every student should try to get at least 10 or 12 from. From what I see, the grades are very nice. So we have a lot of 8s, a lot of students who got all the questions correct. And the majority of students got only 1 or 2 questions wrong. And then we have, that's it. Yeah, I think that's all. Right. That's good. That's good. So the average of the grades was 7. That's very nice. That's very nice. Now let me just open up your results. Can you guys see your results already or not?
Not yet.
No, not yet.
Not yet. That's good. Let me open it up. Now you guys should be able to see your grades.
Yes, yes.
Nice. Are you surprised with your grades or? Nice. So just like to go through the questions together quickly. The first question is, given a large image with a small object foreground and big white on gray background, will the global average global threshold method provide a good segmentation for the object? Simply put, we have a very large image like this, and the object inside is like this. If we take the average of the pixel intensities here as the threshold, we're certainly not going to be able to segment this point. And this is why this is false. Next, given an image with perfect bimodal pixel intensities, right? So basically, it should look like this. This is the perfect bimodal pixel intensities. This is what I just described here. Will the Otsu's method provide a global threshold that is optimal for the image? True, right? So given the assumption it is correct, the Otsu's method will always give something very good because the function that it's using to estimate looks always like this, right? So it's a very convex function, and optimizing it here is pretty easy. There will always be an optimal global threshold for, well, this is my kind of typo, to segment perfectly every image, but it is hard to find. Yes, it is hard to find because it does not exist. So basically, this is false. Adaptive thresholding provides a different threshold for different parts of the image, and this is why it can handle more complicated scenarios. True. I hope nobody got this wrong. The gradients allow us to measure the change in function values. True. We can estimate the derivative of an image with simple filters, allowing us to detect edges much easier. Again, true. Laplacian filter combines the second derivatives in x and y directions in one filter and provides better performances when coupled with Gaussian blurring. True and true. And here, erosion should be used on historical documents to make them more clear and recover their missing parts. This is definitely wrong. false, mainly because erosion takes, for example, something like this. Let's say you have an F that looks like this. Erosion would completely like remove this whole object directly, right? So we should not use erosion on historical data. And this is false. Any questions so far? No, that's very nice. Now let's finish our previous lecture. Here we go. So this lecture we spoke previously, we spoke about the Harris detector. Now we're going to finish basically speaking about SIFT. I'm sure that you have done already SIFT in the labs. Is that correct?
Yes.
Nice. So here we are just going to go through the theory of SIFT pretty quickly, speak a little bit about feature matching, and then the application areas. And after that, we will.
Can I ask something?
Yes, of course. Yeah, go ahead.
Can you please, just for 1 or 2 minutes, can you please go through Harris detector again?
Yeah, of course. Yeah, certainly. Yeah. We're definitely going to go through all the steps or all these images again. No worries. And yeah, let's just come back here. So basically what we're going to do is simply we're going to go through all of these detectors, revise them, and then we will go through SIFT, which is a pretty easy detector and descriptor. And of course, we will speak about feature matching and the application areas of this technique. And after we finish, we're going to create like those mind maps basically for all of them. Mainly, we're trying to build kind of like the relationships between this lecture and the previous lectures, right? So this would allow you to get like some sort of a bigger image. So feature extraction, what it allows us to do. So basically, we identify some points which are most interesting in the image, or the points where the action is happening. And then we just use these describers to basically describe every one of these points which are interesting. And later on, we would be able to combine or to compare these points of interest with other points of interest in other images, right? So for example, we have an image like this and we have an image like this. We can clearly see that both of these hills are pretty interesting for the algorithm. And they usually give the same description. If you have a good describer or descriptor, then you should have like the same values for these points. So later on, you can easily compare them one-on-one and find some sort of matching together, right? So we do some feature matching, and that would allow us to find a good, what is it called? Either a linear transformation or non-linear transformation, depending on what you guys want, that combines both images together like that into something a bit more bigger. And we saw that Visual Slam kind of uses something pretty similar, which takes like walks around, and then from the images, it tries to find the points which are most interesting, describe these points, and then save them for later on. And while it's walking another time, it will be able to compare basically what it's looking at with what it's already saved, and understand its location and kind of reconstruct a good 3D map of the situation or the environment. So feature detectors. First, we'll speak about the Harris detector, right? So the only big question here, or the only like kind of question that really interests us is the following. What makes a good point, or what makes an interesting point, right? Are we interested in like points which are here, or flat points which are just in the middle of the object with basically no change in pixel intensities? Or are we interested in edges? Or are we interested in these corners? Right? So this is the question that we need to ask. For us in the next or in the following in this lecture, the main objects or the main points that we're interested in are corners. That doesn't mean that you can't find some other algorithm that basically looks for these flat regions and well, works well when you are able to compare it with flat regions. But for us, we're going to be working with corners. So meaning a corner is basically a significant change in pixel intensities in all directions, right? So here for an edge, there is certainly a change in the colors between here and here, right? So the image should look something like this, right? And here is the edge. Now the Harris corner detector is trying to basically do this task of detecting corners and using them to kind of represent what the object looks like. So to just put it simply, what we're going to do is we're going to slide a small window around our image. And we say that this window is centered on a good pixel. So basically at every pixel, we have a window centered around it. And we say that this pixel is interesting if basically there is a huge or there is an interesting change in pixels in all directions, right? What does a change in pixel mean? Basically, the difference is large. So this is what a change in pixels mean. So now, given that we are walking, for example, or we have shifted that window with U and V in a certain direction, UV, how will we estimate the change? Simply by using the sum over the change in pixel intensities. Very simple. The only problems, it's very slow and computationally expensive for each pixel and each offset UV, right? So basically for this pixel, we're going to measure the change in all directions with all other windows. Same thing for this one, same thing for this one, same thing for this one, same thing for this one. So definitely going to take a lot of time. So what we decided to do is basically simplify this change in pixels, right? So this I of x plus u and y of and I at x plus u and at y plus v by using a Taylor series expansion, right? So basically what we're going to do is going to approximate it using a first order approximation. Why do we take the first order approximation? Because it gives us very simple values here to calculate. And it's certainly going to get rid of the ixy from the initial function, right? So going to get rid of this one. So this is why we stop at the first order approximation, which is a good approximation in the cases where u and v are not very big. And this is the cases that interest us because comparing, for example, a window here with a window, for example, in the other edge of the image is certainly not going to give us any information about what's happening in that area. So the good measures in shift are always with small values of u and v. Hence, a first order approximation is always going to be good for our function. So simply put, we have the, here we have the approximation of a change. Let's imagine there is just one one-dimensional function, right? So this is the function. And here is our approximation. We can certainly see that around the point x in small directions, this black line can still give us very close values to the original function. Yet it's a much simpler function. So this is what we're trying to do. We're trying to estimate basically this original big intensity function using simple linear combination. So here as we said, we simplify it, we replace it, this one disappears with this one, and we end up with a much simpler value or much simpler function. And in this case, it's not very much dependent on the values of ixy, so it's only dependent on the derivatives in that area. Now we can see that if we kind of expand this term, we will have something multiplied with u squared, something multiplied with v squared, and definitely something multiplied with 2uv, right? This something that we get is the following. So it's the sum over derivatives of x squared this is the sum of the derivative of y squared, and this is the sum of the derivative of x multiplied by the derivative of y. How did we do that? We have seen this in the previous lecture, but simply you just open up this brackets, and you will have like something like this: ix squared plus 2 no, let's do plus 2ix iy uv plus iy squared v squared, right? So here, later on, we see that this sum is only concerning x and y. So basically, we could easily extract anything which is what u and v, u squared. We can extract it from the sum. So basically, it becomes like this: u squared multiplied by the sum of ix squared, and same for the others, right? Pretty easy. Now that we have it like this, so this is the representation of the ellipse equation, and we can represent it as a matrix looking like this. So here we have A, here we have C, and in these 2 points we have the B. Right. Now, just like for simplicity case, we're going to keep these values here, but from now on, let's just imagine that these are A, B, and C. No need to kind of calculate all of this. Keep this in mind, right? So what we spoke about after that is that eigenvalues are going to, of this matrix, are going to help us understand basically if this is a corner or this is a edge. So basically, now that you have an image, or now that you have a kind of matrix that summarizes what's happening around the pixel, right? So this H is going to represent the information happening around, for example, pixel, a certain pixel, XY. H, we're going to process it in a certain way in order to basically extract as much information about what's surrounding XY as possible. So this information that we're going to extract is relative to the eigenvalues and eigenvectors of this, this H, right? So how do we first calculate eigenvalues and eigenvectors? We simply take this formula and calculate for the determinant of A minus lambda I, set it equals to 0. This would give you something that you solve for, like, usually it's just a multiplication, right? Remember, the determinant of a matrix A, B, C, D is always like this: positive minus multiplication here. So AD minus CB. And then you just solve it, set it equal to 0. You would get different values for the lambda, and then replace the lambda in here, each value of the lambda in here, and solve this function in order to find the x or the eigenvector. We have done this already, and I asked Karam to basically give you a small reminder of what determinants are, what are eigenvalues, and all of these things in the lab. So this lab, you're going to get like a bit of mathematical practice. Remember, for example, when we were working with PCA, what we did is we shifted so here's the data, right? So we kind of found a linear transformation that shifts our, what is it called? This, our axis to these two axes, which kind of keep as much information in the first few axes as possible, and the next axis would have as least information as possible, or information change. So this is what these eigenvalues and eigenvectors are trying to give us. So they give you what is the direction of change and what is the intensity of the change. And of course, this is what we're looking for. Sorry. Nice. So after you do the plotting with the first lambda, this is the first eigenvalue, and this is the second eigenvalue, you would find out that the corners always have a very large lambda 1 and lambda 2 for both of them. Edges, they have at least one of them, one of these values as big and the other as very small. And flat regions, which don't interest us, are those which have, basically small lambdas for both of them. Somebody decided to basically combine this chart into like a small classifier that kind of looks like this. Something that gives you what corners are, right? And basically what he wanted to do is to build a function that combines the lambda 1 and lambda 2 in a manner that simplifies the decisions. So here we can see that corners always have a very large response. A negative response with a large magnitude means it's an edge, and a what is it called? A small absolute value for the response means that this is a flat region. Hence, here if you look at the image in here, we usually end up if it's an R or it's a corner, meaning both of them are very small. So this is very big. I mean, this is very big. This is very big. Multiplication gets very big. We minus alpha is usually a small number. Their sum squared is going to be something that is pretty big, but multiplied with alpha, it's not going to influence it that much. Whereas when we are working with edges, for example, we have a small number multiplied by a big number. So here we will have something very small or smaller, right? And then we will have the sum squared. If one of them is big enough, then this sum is going to be very big, and the square of it is going to be even bigger. So a small number minus something very big gives you a negative value. And of course, for very small numbers, small minus small gives you always something small. So this is how he created basically the logic of this function. And the alpha is just usually a empirical value, and you can set it to anything between 0 to 0.25. Usually you could go with what? You can see your, I don't know, Zoom is showing me some weird stuff. Anyway, so usually you'd go with a value of 0.05. So this is how the Harris detector looks like in practice. So these are the points that we get after in the end. And this is how its response is looking like. This is the response function. Remember, every single point has an H matrix. Every single point has 2 lambdas or eigenvalues for the H, and every single point would have an R. So this is how we got this beautiful image. After you make a thresholding, of course, you get rid of the smaller values and keep only the higher values. And then you do this non-maximum suppression. Does anyone still have like problems with non-maximum suppression?
Yes, actually.
Okay, so
I remember we covered it in practice, but it was very fast.
okay, let's do it like together. So non-maximum suppression is a simple algorithm. You go through all the points. You have a list of all of these points and their values, right? So for example, sorry, let me go back here. So all of these points have a certain value. So for example, here it's, let's go here. Yeah, much better. So after we thresholded them, we keep the value itself, right? So for example, here we have 255. Here we have to 150. We keep all of these original values. First, we start by looking for the highest value possible. So we found something like 250. What we simply do, all of its neighbors, we set them to 0, or we remove all of its neighbors. Okay. All of its neighboring points, we remove them. Then what we do, we go back and find from the points that were not removed, what is the highest value. So for example, we found that this other value is 240. We repeat the same process. Every point around this 240, so definitely it's going to be smaller than 240. Every point around it, we will remove it. And we continue this approach until we finish all the points, right? So this is what non-maximum suppression does, right? So at every single, let's call it neighborhood, we keep only one point of interest. So this is what non-maximum suppression does, right? Now, an improvement of it is basically, instead of using the this, either you belong inside the window of change or you do not belong. Now we're going to kind of weight it using some Gaussian distribution, right? So the further you are, the smaller it is, the closer you are, the more influential you are. So to summarize the process in general, so we compute the derivative in X and Y, do the multiplication of derivatives, then do the sum of these values just for A and B, remember those, A and B and C, and then create this H matrix of A, C, B, B. From this matrix, we calculate the eigenvalues. From the eigenvalues, we calculate the response matrix. From the response matrix, we threshold, and then we do the non-maximum suppression. And there you go, you have the points of interest, or you have your corners. This seventh part, we will be doing it in the next, basically in the following part. So this is the Harris corner response. So usually it's pretty good or pretty invariant for rotations. The eigenvectors certainly will change, but the eigenvalues will not change for the same object in the same area, right? Or like the same object, but like rotated or something like that. It's not also very invariant to intensity changes. So basically, if you are working on an object at light, and then you work on the same object in the morning, at night, it's going to give you very similar results. Sorry. It's not scale invariant because a corner in here is just an edge in this edge. Now this Shy-Thompson algorithm or corner detector is pretty simple, but the response is, instead of having a complicated function like this, we just have minimum of lambda1 and lambda2. So basically in here, if the minimum is big, that means both of them are big. Simple. Now let's go to scale invariant feature transform. Since you guys already did this, so you already know what's going to happen here. What it does is it summarizes different parts of the image in a special like feature vector. So let's continue and get to it, right? So there is two different parts of it. So there's the detection part and there's the description part. The detection part starts with scale space extrema detection, then key point localization, and then orientation assignments. We will see what each one of these in the next slides. And then the last one would be the key point descriptor. Basically, we're describing all the key points as some high dimensional vector, but only one dimensional. So basically like this, right? In the 1D. Yeah, this one would give us something that is more scale invariant detection. Basically, if this is a corner and this is a corner, we're aiming to build a window size that basically works for this one and works for this case, right? So this is the goal of SIP. So what we're trying to do is, if we can manage to find some sort of a function, right, that looks like this, a function that kind of based on scale or the region size, it gives us what is the most optimal window size, right? So if we scale the image again and again and again, if we can find a function that gives us the optimal or evaluates the optimality of a what is it called, a window size, then we can use this to basically decide what the window size is for every single key point. And this is what we're trying to do. So this is what a bad function would look like with a very large region. This is lots of local maximums, and this is what a good function should look like. This function that we have tried to make is pretty related to what is it called, variable scale Gaussians. Basically, we will be applying the idea that we have seen before of, applying this idea of Pyramids, again, something pretty similar to it again. So what we will do, we will take an image, give it multiple scales of this image, right? So operate on multiple scales of the image. First is the initial size of the image. And here we are working with a different size of that image. So smaller size, and then smaller size, and then smaller size. And then for each one of these different sizes, what we're going to do is we're going to blur it on different levels, right? So here, for example, we have, let's say, original size, original image. Original size blurred with a certain, with sigma equals to 1. So not a very big blur. Original size with sigma equals to 2. And then original size with sigma 3, 4, 5, 6, 7, 4, so on and so forth. And then after that, we have in the same feature pyramid or same image pyramid, we have the smaller size or half the size with blurring equals to 1, half the size blurring equals to 2, same, so on, so on, so on and so forth, so on and so forth, so on and so forth, right? After this, what we do is we will calculate the differences between these two values, right? So basically what it's trying to do is if a pixel here was quite interesting, regardless of the scale of the, what is it called? Not the scale, regardless of the blurring, right? So when we combine it with this neighborhood, it's important. When we combine it with this neighborhood, it's important. When we combine it with this neighborhood, it's important. That means it's a pretty important one. And the same thing is for the scale. So when we are working on a smaller scale, it's still very interesting. And when we are working on a very large scale, it's pretty interesting. But the most important scale was, for example, at this region. So this one has the highest scale of importance. So this allows us to basically compare the local extrema of a point, but at different versions, right? So instead of comparing it at the image itself, now we're going to be able to see it at different levels of blurring and at different scales of sizes. So this gives us the key point localization part of the algorithm. Just some, I think we should understand that. We have 12 minutes, so I don't think we could finish this pretty completely. But let's go for it, right? So just to finish the lecture quickly, and then we will go back through it maybe next time again. After we finish every point, we find the points of interest, as we said, using this algorithm of localizing the extremums in or localizing the extremums in our different scales. Now we're going to kind of represent these images. So first we will take the orientation of the gradients and the magnitudes. We built our histogram of oriented gradients, and then we put it on 36 bins covering 360 degrees. And then we take only we only use those which are in the region from 80 to 100%. Or to the maximum, right? The key point descriptor is pretty simple. It's very basic, very similar to what you guys have seen before. So we take a region, split it into 4x4 batches, and then each one of these batches, we split it into 4x4 batches again. And then we create this, what is it called? Histogram of oriented gradients for it with different, you see, different directions and different, so different bins and different amplitudes for each bin. So this gives you an 8x8, so an 8 vector, a vector, one-dimensional vector with 8 values. Same thing here, same thing here, same thing here. Then when you combine them all together in the one-dimensional vector, you will have 128 values. And this is the values that kind of will describe your point. At the next stage, we'll be seeing how do we use this for comparison, right? So SIFT is pretty robust. So they're saying that it can handle changes in viewpoint up to 60% change in the viewpoint. It's very good for changes in illumination, and it's fast and efficient. There are different variations of the algorithm, but what's mostly important for us is this feature matching technique. Once you have found the different points using this scale invariant technique, Then you describe them with our histogram-oriented gradients technique. What you can do is you can compare them with another image of the same part and basically build this matching between all of them, right? So if you know that this point is represented in a certain manner, has a certain feature vector, you could easily compare it with the other points and find its location in somewhere else, right? Of course, there are cases where you can never really do that. So this is the zoomed in version of this one, but where is it in the image? You will never be able to find it. Pretty difficult, right? So the feature matching algorithm uses the nearest neighbor algorithm based on L2 distance. It's pretty simple. Basically, you calculate the L2 distance between every two pairs, and you take the closest one. But there is one big problem is that the second closest match may be very, very near to the first match, right? So probably you would have something very similar to it, like this. So this was your image. You found it here, and you found something else here very close to it, and something else here very close to it. To solve this problem, instead of using just the distance itself, we're going to use the ratio. Closest distance to second closest distance will be taken. So again, what we do, define the distance function that compares the two descriptors. The two descriptors are just two feature vectors, right, for every point. And then test all the feature vectors on the target image and find the one with the minimum distance. So very simple approach, but it might have some problems when you have like repetitive styles in this case, for example, here. Whereas when you are using, for example, this better approach of the ratio distance, kind of gives you something a bit less ambiguous. So this is just an example of how this works in real life. So you can see we found these points of interest in the image, and then we found them again in this place. And what we just did is we calculate their descriptor, and then we can compare the descriptors of these parts with these parts. And you can easily now see that it's first doing this feature matching. So basically allows you to combine two images together, but more importantly, it's able to do object detection, right? So it's pretty similar to an object detector where you are taking one object and finding its location in a much larger image. Now, how do we evaluate the performance of our feature matcher? This is a very simple technique, right? So very similar to what you guys have been doing in machine learning. You take the feature distance. So this is, for example, the ratio between the 2 points. We can clearly see that this is wrong. This one is definitely correct, so small feature distance, and this one, same thing too. So what we do is we calculate the true matches that the algorithm is giving us, we calculate the false matches, and then this would give us the true positives, and for example, the recall, which is true positives number the match divided by the positives in general, and the 1 minus the specificity, which is just the false positives divided by the unmatched features or the negatives. This would allow you to do the same thing or the same evaluations as before. So you can use accuracy, you can use F1 score, you can use area under the curve, and all of these different measures of. Oh, we still have time. Surprising. Yeah. So we have lots of applications of this technique. So the first one is image alignment, 3D reconstruction, motion tracking, object recognition, indexing and database retrievals, and robot navigation. Now that we have this done, I really want to finish up with one simple mind map that kind of combines the topics that we have seen together today. So let's open them up together here. This is lecture 4, this is lecture 3, right? Let's go. So in lecture 3, what we have seen is the following. So we spoke about binary vision. We spoke about global thresholding. We saw that the first algorithm, it's pretty difficult to find threshold. One algorithm that could be used is the bimodal histogram combined with Otsu's method. Sorry. Right? Sorry, like this. With Otsu's method. And then we said that for global thresholding, there is band thresholding. And then there is the semi-threshold. We also saw that there is something called as local thresholding or adaptive thresholding. And basically it gives you local thresholds for each window. And we can improve it by adding some Gaussian noise or some Gaussian blur. Nice. Did we see something else? Yes, erosion and dilation. Then we saw that there is two of these morphological operations. We have erosion with a big O here, or with an interesting O, right? And we have dilation where the D is the biggest, like this. Yep. And then we could combine these things into, sorry, opening and closing. So this is lecture 3. Let's take this and build lecture 4 next to it. For lecture 4, what we have seen is connected components, connected component labeling, object detection using template matching, image pyramids, and then we have seen histogram of oriented gradients, and we finished with active contour models. So for this one, let's call it object detection. Let's say connected component labeling. Yeah. Connected component labeling, pretty simple technique, similar to clustering, allows you to find objects which are connected. For object detection, we spoke about template matching and how it could be improved using image pyramids, but it is, and how it uses basically MSE or cross entropy. But it's pretty bad since it doesn't really work with different viewpoints and interclass variations. Then we saw HOG on histogram oriented gradients. So it describes images in a vector form. And it does that by calculating the or binning the gradients amplitudes based on their direction. And this is how we basically build the descriptor of the images. And then after that, we spoke about active contours. And we saw the snake algorithm, the snake algorithm, and we saw the expanding, what is it called again? Balloon, yep. Expanding balloon algorithm, and then we saw the GVF. Very well. So this is kind of like a small summary of what we have seen in the last 2 lectures. I will clean this this up a little bit and send this in the Telegram channel. Thank you guys all for attending. If you guys have any questions, please feel free to ask me or ask Karam. He's going to also give you a small revision over all the concepts that we have seen together. And good luck. Have a great week.
Thank you. Goodbye.
Thank you.
Goodbye.
Thank you. Goodbye.
Goodbye.